So one of the things we talked about when we discussed dissolving was the fact that dissolving a solid happens in two processes. The first is that the solid must dissociate. So that's a process of collision. The solvent molecules are going to come in, collide with the solute, and break off small pieces. For a molecular solid like sugar, that would be breaking off molecules of sugar. For an ionic solid, like we have in our picture, potassium chloride, we're actually going to be breaking off individual ions from the solid ionic lattice. Sometimes I say dissolving things is like a tiny little horror show in a beaker because the solid is being ripped apart by the solvent. Once the molecules have or ions have dissociated, they've broken loose, then there is the process of solvation. And solvation is a process of intermolecular attraction. Intermolecular means like the interstate. It is two different molecules interacting with each other. In this case, in our picture, the water molecules are going to wrap around the ions and solvate it. And you'll notice that the water molecules are pointing at the ions in a particular way. They are hydrogen side towards the negative chlorines and oxygen side towards the positive potassium ions. And so there's something to think about here as to why that might happen. Well, if you remember, water is an extremely polar molecule. It is lopsided. There's more electron density around the very electronegative oxygen with its two lone pairs than there is around the hydrogen. So water has a lopsided electron distribution. It has a partial negative side, the oxygen, and a partial positive side, the hydrogen. And so you can see the partial negative oxygen is attracted to the positive ion. The partial positive hydrogen is attracted to the negative ion. This is an ion dipole force, something that we'll talk about in Unit 3 in AP Chemistry. So molarity is what we use to distinguish the concentration of a solution. Molarity is in moles over liters, or what's often more useful to us because we usually do reactions in small scale, is millimoles over milliliters. That way we can deal with small numbers instead of having to deal with numbers that are so tiny we must put them into scientific notation. Algebraically, you can rearrange that formula to get any information you need. If capital M molarity is millimoles over milliliters, and if I multiply both sides by milliliters, I'll get molarity times milliliters is millimoles, or molarity times liters is moles. And you can see from here, if I need to get the milliliters by themselves, I would end up with millimoles divided by capital M molarity would get me the milliliters that I need to get that number of millimoles with that concentration. And we do use the second one a lot because we do most reactions in solution. And that means we can't just get a mass of a solution because most of the mass is water, not a chemical. So we use molarity times volume to get into moles or millimoles so that we can use that in stoichiometry. So here's a little example problem. You'll notice here it's asking for the bracket here, NaCl. In chemistry, a square bracket like that around a chemical species indicates molarity. It's kind of a chemistry shorthand. And so there will be times when it will be very important that we make sure that we do not use this bracket where it's not needed, like if we're dealing with a partial pressure for a gas, because if you put that in brackets, you are automatically telling a chemist that you are dealing with millimoles per milliliter or moles per liter, capital M molarity. Well, the problem with this problem is it's in grams, not in moles. But since we have the molar mass, we can easily do that. This is carefully chosen numbers. 5.84 is obviously 10% of the molar mass, so that'd be 0.1 moles. And I could convert the 250 milliliters into liters and use moles over liters, or I can convert that into millimoles and use milliliters, but I have to be consistent. So 100 millimoles over 250 milliliters means that I have a molarity of 0.40 molar. Probably should be 0.400 molar because I have 3 significant digits in my mass here. So let's look at a solution of calcium hydroxide versus sodium hydroxide. And oftentimes, especially with something like sodium hydroxide, the sodium is usually a spectator ion. And so most of the time we'll be thinking about the ion concentrations a little differently from each other. So the reason I've started by talking about the dissociation and solvation process is to think about what happens in this reaction, which is showing the dissolving of sodium hydroxide. I take solid sodium hydroxide, and those ions are dissociated. They're pulled apart first to form separate sodium ions and hydroxide ions, which are then solvated. They become aqueous. So if I say I have a 0.1 molar solution of sodium hydroxide, there's 1 sodium and 1 hydroxide. So if I have 0.1 moles of this per liter, I would have 0.1 moles of sodium and 0.1 moles of hydroxide. But what would happen if I had a similar equation for the dissolution of calcium hydroxide? Well, it would look like this. I would have solid calcium hydroxide, and it would dissociate. I would pull off a calcium ion. Then I would pull off a hydroxide ion. Then I could pull off the other hydroxide ion. Those hydroxide ions are going to be pulled off separately. They will dissociate into the solution on their own. So when I look at the formula, I can see from the subscript that 1 calcium hydroxide molecule is going to give me a calcium ion, but it will give me 2 dissociated hydroxide ions. So this is a different situation then. If I have a 0.1 molar solution of calcium hydroxide, let's think about what would happen when this dissolves. Now, in this case, I have a little bit different situation. I have 0.1 moles per 1 liter of the calcium hydroxide. But from this formula, I can see that 1 mole of calcium hydroxide contains 2 moles of OH minus ions. So I find that my concentration of the OH minus, the hydroxide ion, is twice as big as my concentration of the entire thing. So if I have a 0.1 molar solution of calcium hydroxide, I get a 0.2 molar solution of hydroxide ions because 2 hydroxides are dissociated and pulled off of every molecule of calcium hydroxide. So let's take a look at a problem like this. So this says that I am going to combine 2 solutions together. I'm going to assume that the volumes are additive, and I'm going to try and find the molarity, because I'm in square brackets, of the calcium ion in the new solution. So I'm going to have to kind of break this up by parts, because I'm going to get some chloride ions from the sodium chloride solution and some chloride ions from the calcium chloride solution. So starting one by one, how many millimoles of chloride ion would I get in the sodium chloride solution? Well, for every 1 sodium chloride, I get 1 chloride ion, so the molarity of the chloride ions is the same, 1 to 1. Since millimoles is molarity times milliliters, I get 0.2 times 15 milliliters, means that this solution is going to contribute 3 millimoles of chloride ions. Now I'd like you to try doing this. How many millimoles are in the calcium chloride solution? You can pause this and come back to it. Well, this is like the one before. For every calcium chloride ion or calcium chloride molecule, I'm going to get 2 chloride ions. So the molarity here is going to be twice as big because there are 2 ions for every 1 molecule. Or you could do this by getting into millimoles of calcium chloride first, and then you'll discover that you would end up doing the same thing, multiplying by 2. So the millimoles is molarity times milliliters, so 0.6 molar times the 15 mils is 9 millimoles of chloride ions. So from this information, I should be able to find the total molarity of Cl-. The total number of millimoles would be 9 millimoles from the calcium chloride solution plus 3 millimoles from the sodium chloride solution, or 12 total millimoles. The volumes are additive, so 15 plus 15 is 30. And the total molarity would be the millimoles divided by milliliters. 12 divided by 30 gets me 0.40 molar. So this one is actually a lot faster than you would think it is. Logically, the first thing we're going to need to find out is what is the molarity of the original solution. We need millimoles divided by milliliters to get molarity, and this is again conveniently picked numbers because 4,000 milligrams are 4 grams. The molar mass is about 40 milligrams per millimole, so this comes out to be about 100 millimoles. And 100 millimoles over 100 milliliters would be 1.00 molar. But finishing this requires that we remember the definition of a solution is a homogeneous mixture. That means the molarity is the same in the top 50 milliliters as it is in the bottom 50 milliliters in any sample from anywhere. So if we know what the original molarity is, we know the molarity of any part of the solution. So the molarity would be exactly the same. So here's my last little question. This is kind of a thought idea here. I have 2 situations. In the first solution, I take 1 mole of sodium chloride and dissolve it and add water to make 1 liter of solution. In the second one, I have a liter of water and I dump in 1 mole of sodium chloride. Is the molarity the same? Well, the first one's fairly simple. We have 1 mole, which we use to make 1 liter, so that's 1 molar. I'm guessing that since I asked the question, you're already figuring that the answer is not that simple for the second one. It would not be the same. And that goes back to the fact that sodium chloride is matter. It has mass, and mass takes up space. So if I just add a mole of sodium chloride to 1 liter of water, it's going to dissociate and solvate and take up space. So that 1 liter of solution will now be larger than 1 liter. So it will be slightly different. Or you could even think about it as if you had 1 liter up to the brim and then you dump salt in, it's going to overflow because sodium chloride takes up space even when it's dissolved. So when you go to make a solution, it's important that you dissolve the solute in a smaller amount of water first. If I were going to do this, perhaps I would say I would get 500 milliliters, half of my volume, and dissolve the sodium chloride in that first. Then I would add water until I reached the desired 1 liter of solution.